All right, so hello everyone. I'm really excited today to invite Dr. Debnandini Mukherjee. She's a student of physics. She's a researcher in physics as well. She's presently working in University of Alabama, Huntsville, and she's also working with NASA at the moment. She will say more about it, I am sure, on the way. And if I'm not totally wrong, she was actually part of the LIGO project, which is responsible for experimentally verifying the existence of gravitational waves. Is that correct, Debnandini?
Yes, yes.
So, in fact, as far as I know, that the paper that actually went on to win the Nobel Prize, they had like a lot of researchers were there in that particular list of co-authors, I think, or co-scientists, and Debnandini was one of them. Is that correct?
That's correct, yes.
Okay, that is correct. Okay, so if you can learn more about gravitational waves, if you want, in the internet, I'm sure that Devnandini might be speaking a little bit about that. I don't know our content for today, but I'm really excited to have her with us. And at the end of this particular talk, please feel free to ask any questions. Those of you who have joined a little bit late, she also mentioned that she'll be okay with taking up questions which are a little bit career oriented or stuff like that. So if you are interested about how to go about with physics in the long run and so on, feel free to ask those questions. Again, a big welcome to all of you, and you in particular. Please go ahead and start the session. Thank you.
Okay, so I think I will start.
Yeah.
So, if I were to ask you what is the heaviest object we can observe, would you think of our planet or the largest planet in our solar system or perhaps our sun? But what if I tell you that we can observe objects now that are tens to hundreds of times as heavy as our sun? So, hello everyone. As Shani just introduced me, I am a postdoctoral research assistant with the University of Alabama in Huntsville in the US. And I work with the NASA Marshall Lab here in Tyson Littenberg's group. And so I'll tell you a little more about what I do. So I have been working on gravitational wave data analysis within the LIGO Virgo Kagra or LVK collaboration. And I have mainly been working on searches for compact object coalescences using a search algorithm called GST-LAL. And so we use pre-computed signal templates to search for gravitational waves. And I have been involved in LIGO Virgo's first, second, and third observing runs, and also the ongoing fourth observing run. So in my present postdoc position, I have recently started working with the LISA consortium as well within NASA. So my PhD was from University of Wisconsin in Milwaukee, which is the same school as where Ashani went for his PhD. And then after that, I've done a postdoc in Penn State University, and then currently I am at University of Alabama and NASA Marshall. So now let's talk a little bit more about gravitational waves. So let us look at what they are. So they are ripples in space-time caused by accelerating objects, and then these ripples will propagate as waves at the speed of light, and they were predicted by Einstein in 1916 in his general theory of relativity. So this simulation that we are about to watch, it depicts the birth 1.3 billion years ago of the gravitational waves that were discovered by LIGO on 14th of September in 2015. So here, two black holes about 30 times the mass of our sun are seen to in spiral around each other and then collide and merge. So in bright green here are the regions where the waves stretch the space, and in dark green are the regions where they squeeze the space. As the black holes approach each other, the waves start to get shorter and the separation between them gets shorter, giving rise to what scientists refer to as a chart. And then these two black holes collide and merge into a new black hole, bringing the waves to a crescendo. And this newborn black hole then vibrates briefly and becomes quiet and stops generating waves. So these waves will eventually depart from the black hole's vicinity and then they travel out into the universe. And these waves are the ones that carry the news of the black hole's collision and give us more information about it. So, in John Wheeler's words, matter, or in other words, energy momentum, tells space-time how to curve, while the curvature of space-time tells matter how to move. And this is the core idea presented in what we know as the Einstein's equation. And then these gravitational waves are solutions to Einstein's equations, and they have two different modes of vibration. The diagram here shows the two uh, modes affecting space-time as they pass through. And here the effect is shown on a ring of beads. The plus mode, denoted by H plus here, will distort space-time along the orthogonal directions. And the cross mode, denoted by H cross, distorts space-time in the diagonal directions. So this simulation here will give us a little more idea about what we see in data when these coalescences happen. So the simulation here shows the inspiral and collision of two black holes. The top portion of the frame shows the horizons of the two black holes. The middle portion of the frame shows the gravitational waveform projected onto one of LIGO's detectors. And the bottom part here shows the frequency of the gravitational waves, and it's gradually increasing from about 35 hertz to about 700 hertz as they inspiral and merge. So, um, so now I'll briefly describe the workings of the laser interferometer that makes observation of these signals possible. So the LIGO detectors are modified Michelson interferometers that are L-shaped, and they have 4-kilometer long arms. So light from a laser, as you will see in this video, is split by a beam splitting mirror so that the two split beams travel down the two arms of the detector and are reflected back by the end mirrors. The reflected beams then interfere and enter a photo detector. The default configuration of the system in the absence of gravitational waves is such that the interference is destructive and no light escapes into the detector, which is what you see right now. But in the presence of a gravitational wave, there is a relative change in the length of the detector arms. And then this causes a difference in the phases of the interfering waves. And so light is then seen to escape into the photodetector, and that is read off as a current. And then the amplitude of this current is proportional to the relative change in length of the arms of, or what is also otherwise known as a strain. And then this in turn is proportional to the amplitude of the passing gravitational wave. So, so this slide here shows the locations of the ground-based LIGO-like detectors, so at present, and the ones that are also planned in the near future. So they comprise these L-shaped laser interferometer detectors, which together form a network. So in the US, we currently have the LIGO Hanford detector in the Northwest, and then the LIGO Livingston detector in the Southeast. In Europe, we have the Virgo detector, which is the only operational detector. We have a smaller detector called GEO in Europe, but it's mostly used for calibration purposes. And then we have two upcoming detectors in Asia. So there's going to be the Kagra detector in Japan, and then the planned LIGO detector in India. So let us do a little recap of what we have been seeing so far using LIGO and Virgo. So LIGO Virgo has had 3 observing runs or data taking periods so far. So with these detectors, we cannot continuously take data. We have something called commissioning breaks in between. That's the time when the detector goes through any kind of improvements, any fixing we need to do. And so each of the periods when data is being taken are called observing runs. So the first observing run, which we abbreviate as O1, lasted between 2015 and 2016. O2 was between 2016 and 17, and then O3 went between 2019 and 20. We are currently in O4, which started in the May of last year, and the first part of O4 is just concluded, and we are in the middle of another data taking break. So here we see the observations made by LIGO Virgo up until the end of that third and last complete observing run. And this constitutes the third gravitational wave transient catalog. So we basically publish catalogs of whatever we have observed, much like people used to in the past in case of fashion magazines and I don't know other kinds of merchandise. This was kind of a way back. Don't bother about it if you don't relate. But so in blue here are the black holes that are observed by LIGO and Virgo. And in orange are the LIGO observed neutron stars, and in yellow are the neutron stars that were known just from electromagnetic observations. So 90 compact binary object coalescences have been observed up until the end of the third observing run. And the heaviest merger that was observed up until then is also shown here in red. And we will talk a little bit more about this particular event. But so this figure does not include the newer black holes we have observed in the fourth observing run. So we have even more down the pipeline. So let us take a quick look at what our search targets are. So this slide here shows a plot between the component masses of some of the coalescing binaries. So by binaries, I mean pairs of compact objects like black holes or neutron stars. And the compact object searches that we are sensitive to is what is shown here. So the heavier mass called M1 here is on the x-axis, and the lighter masses or M2 is on the y-axis. And then each point on this plot represents some of the binaries that we are sensitive to. And there are about 1.7 million systems represented on this plot. So the lower mass region here below a total of 100 solar masses are what we collectively call the stellar mass objects because their masses are more like known stars. So this includes the neutron star binaries or BNSs, the neutron star black hole binaries or NSBHs, and the black hole binaries or BBHs. Above a total of 100 solar mass in this higher mass region are what we call the intermediate mass black holes or IMBHs. So this whole set of binaries that you see here, it also corresponds to the set of signal templates. And we call such a collection of templates a bank. And this is also used by algorithms like GST-LAL, which I work with, to filter the data to look for any significant correspondence. So the third observing run, it began in the April of 2019, and on 21st May 2019, we observed the heaviest gravitational wave event in LIGO Virgo data up until then. So it resulted in a 142 solar mass remnant from a pair of 66 and 85 solar mass components. And so the gravitational waves here in the rest of this talk will be denoted by GWs, and then they are followed by this date of observation. So it's 1905-21 because it was observed on 21st of May in 2019. And so then this figure here compares this event against the other public heavy mass mergers that were known up until that point. And the total masses are on the y-axis here. So we can see that for the first time, we observed a remnant that lay in a mass range that has long been postulated to be occupied by the intermediate mass black holes. Ashani, if there's a question or a comment, let me know. I can see the chat.
No, there is no question up to
Okay.
now, but I was about to ask a question. Is that okay, or should I?
Yeah, go for it.
Okay, so so just a layman's question. I see that at 85M and a 66M is colliding to create a 142M. Is that correct?
Yes.
So I noticed that there is a loss of mass. What's happening to that lost mass?
So that's the energy that is emitted in the gravitational waves.
Oh, I see. Okay. Oh.
So, shall I continue?
Yeah, please go ahead.
So, yeah, so I was going to talk a little more about intermediate mass black holes and IMBHs because a large part of my career so far has been dedicated to these very mysterious types of black holes. So, So while stellar mass black holes are what we have mostly been observing with within LIGO Virgo data, and they have masses less than 100 solar mass, the supermassive black holes that are known to occupy the centers of galaxies have masses greater than 10 to the 5 solar mass. The intermediate mass black holes were theorized to occupy the space between them, and then they have putatively been theorized to be an in between formation step through hierarchical mergers. And so their observation now then raises the question as to whether these IMBHs could be a missing link between these two widely separated types of black hole populations. So it is uncertain as to how exactly IMBHs are formed. And a few of the possible formation channels found in the existing literature are discussed in the publications that we have sent out. But then, in the interest of context, I wanted to talk about a few of them. So they could be IMBHs could be formed from the direct collapse of massive first generation population 3 stars, or from the multiple mergers of stars in dense young star clusters, or mergers of stellar mass black holes in globular clusters. So another important aspect of GW 190521 event is that the heavier or the 85 solar mass component, it lies in a proposed gap in the mass distribution of black holes. And this gap is called the pair instability supernova based gap, or PISN gap. So what that means is theoretically, such black holes remnants are not expected to exist from the direct collapse of massive stars, which is usually how black holes are formed. So this 85 solar mass black hole could not have been formed from usual astrophysics that was known to us. And so its observation then raises the question as to whether this component that lies in this proposed PISN gap could have been formed from the hierarchical merging of two smaller black holes. So this is not a formation channel that we were um, as certain about before. So more discussions on the possible implications and formation scenarios are discussed in publications that we've written after the observation of this event. But then again, more observations of similar black holes will give us a clearer picture as to how they are actually being formed. So no significant IMBHs were observed during the first and the second observing run, but I will briefly describe the search for IMBHs in the last or the third observing run. So we searched the full O3 data using three different search algorithms to look for any other marginal IMBH triggers. And for this, we used data from three different observatories, the LIGO Hanford, LIGO Livingston, and Virgo. There's an IMBH group within the LIGO Virgo collaboration that searched for such IMBH binaries and published a combined search result using three different search algorithms. So the GST LAL and PyCDC pipelines here comprise the modeled search methods or algorithms. They use general relativity based simulated templates for expected signals, like I was saying earlier, and then they put them in a collection or a bank and cross correlate them against the data to look for a significant match. So this process is called match filtering, and it comprises a modeled search where you already have an assumption about what the signal will look like. Whereas the coherent wave burst or the CWB technique is only partially modeled. They don't assume much about what they're going to see. So the results of this combined search has now been published, and then my focus, however, on this work was on the GST-LAL search algorithm. So a little more about that. So as I was pointing out earlier, on left is the collection of search templates or the template bank used to search the full parameter space of compact objects by the GST-LAL search. And on right is the bank that was used for an IMBH focused search. So I led the studies aimed at designing of the search and also conducted the analysis. So to give you a little more of an idea about the nitty-gritty of how this works, so I wanted to show some examples of templates here. that you will see templates here for 3 different observed gravitational wave events. And these are the model signals that the search is trying to find in the detector strain data. So these template waveforms for these different binaries are placed in a bank like I showed earlier, and then they're cross-correlated against the data to look for signals. So this video is going to give us an idea of how it shows the process of match filtering with a single template from a bank, and then it falls upon a signal in the strain data and produces a peak in the signal to noise ratio above. So in the upper panel is the signal to noise ratio, and in the lower panel in black is the data, and the pink magenta thing is our template. And you will see as it falls upon the data, it creates a peak in the SNR, signal to noise ratio. So that's how match filtering works. And so here is a list of the most significant triggers from the combined search using 3 different algorithms for the IMBHs in the third observing run. They've been sorted by their significance. So we found that GW 190521 remained the most significant trigger, and we did find lesser significance triggers, but they were mostly turned out to be of noise origin. So improved detector sensitivity, updated search methods, and also the detection of at least one IMBH allowed us to obtain a revised bound on the rate density of IMBH binaries. So by rate density, we mean the rate of merger of IMBH-like binaries in the observable universe. And this rate is important because this is the only observable quantity we can see today. These mergers happened millions of years ago, and we are seeing them now because this is how long the gravitational waves took to reach us. But then what we can assess is the rate of the mergers of these objects, and that can tell us a lot about which type of astrophysical theories are correct and which ones are not. So they are used as a validation parameter. So assessment of these rates is important. So how we do that is here. Is that a question?
Yeah, there is a question, and I think Sanchit Kumar is asking what will be the speed of these gravitational waves?
Oh, they travel at the speed of light.
They travel at this speed.
Yep. So yeah, so what we do is a simulation study to assess the rates of these mergers. So to do that, we mix in a bunch of simulated signal waveforms into the strain data, and then we run our search algorithms, and we retrieve all those signals that we had mixed into the data. And then the rate of recovery of the simulations is an important thing here. And so that is proportional to the averaged volume in space and time, and that's measured in gigaparsec cube here, to which the search is sensitive for the targeted IMBH binary source. So the sensitive time volume is proportional to the time volume in which we actually make our simulated injections, and that is weighted by the recovery fraction of these simulated signals. And then this is used to compute this 90% rate upper limit on merger rate densities. So also to do this study, we do not use a specific mass model for the simulated signals because we don't have a clear idea about how the IMBHs are distributed in space, since we don't really understand how they are formed. So instead, what we do is we simulate a suite of IMBH binary waveforms for discrete points in the parameter space, and we include generically spinning black hole components derived from something called numerical relativistic simulations. So this part is a little bit dense, but I'll tell you the main takeaways here. So this is a slide that represents the rate density estimates for the simulated sets, and they are shown in their component mass planes. So the left panel here is for spin-aligned systems, the right panel is for precessing simulations, and then each circle here corresponds to one type of IMBH binaries in the source frame that we are sensitive to. So in general, we found an increase in the sensitive time volume of the combined search compared to results before, and this is expected because we have increased sensitivity over time. The detectors become more sensitive as we work on them. And then we also found our most stringent rate calculation to be 0.06 per gigaparsec cube per year for equal mass IMBH binaries with a total mass of 200 solar mass. And this estimate was 3.5 times more stringent or 3.5 times more strong or believable than what was placed before. And that's kind of how science advances. You make estimates as you get to know more about the universe. You reject some theories which don't align with your observations, and you keep the others that do align. And so you keep making more stringent claims as you move forward in the field. So some of the key finds of this study was that GW 190521 was the only major IMBH that we observed in up until the end of the third observing run, and its primary was interestingly found to be a black hole in the pair instability supernova gap. And then the O3 data was searched more thoroughly using the model as well as model independent searches. And we reported some of the more significant marginal triggers. And so then also we updated the merger rate density estimates, and they were found to go through an improvement by a factor of 3.5 as compared to what was found before in the first and the second observing runs. And then observation of more IMBH-like events in the future will help us understand their formation mechanisms a lot better. So I will talk a little bit now about the other part of the compact object space, that is binary neutron stars. And this is where what I call dwarf in the name of my talk comes in. They're just dwarfs in the sense that they are small. They're not white dwarfs. So I'll talk a little bit about binary neutron stars here. So we observed the first neutron star merger on the 17th of August in 2017. So hence the name of the event is GW 170817. And then this event was not only observed in gravitational waves, but as this poster here suggests, it also led to something called a kilonova, and we'll see what that is. And hence it had an electromagnetic counterpart observable initially in gamma rays, then in optical light, infrared, ultraviolet, X-rays, and finally in radio waves. So observations of such events in various wavelengths and multiple channels can help us learn more physics than what can be found using just the electromagnetic observations alone or gravitational wave observations alone. So this animation here that we're about to see captures the phenomena observed over the course of 9 days following the neutron star merger known as GW 170817. So let us take a look at it first, and then we'll talk about it. So what you start to see here initially are two neutron stars in spiraling, and then the radiations include gravitational waves, which are shown in these pale arcs, a near light speed jet that is produced in gamma rays, that is what is shown in magenta. And then this huge explosion is what is called the kilonova, and it produces the ultraviolet, optical, infrared emissions, which are shown in various colors like violet, blue to white to red. And then finally, the X-rays are shown beaming towards Earth. So so this is a spectacular phenomena that comes after the gravitational waves. And so here, this slide basically summarizes the gravitational wave and electromagnetic observation efforts for this event. And this animation shows how LIGO, Virgo, and the space and ground-based telescopes zoomed in on the location of GW 170817 by combining data from the Fermi and integral space missions to gamma ray observatories with the data from LIGO and Virgo. So, so let's just start to look at this. So initially we will see in blue the the gamma ray telescopes detecting the event. In green are the LIGO detectors that you will see in a second. So then this common region is where the visible light telescopes searched a large number of galaxies, and that region corresponds to about 30 square degrees in the sky. And then they finally revealed a galaxy called NGC 4993 to be the source of these gravitational waves. And so this process of zooming in on the location of the source is called sky localization. But in this case, certain things happened that we were not super prepared for. One is the gravitational wave alert was sent out about 40 minutes after, and then the sky localizations were sent out about 5 hours later. The manual observations could not start until 8 hours after merger. And then the source by then actually was below the horizon for many of the electromagnetic telescopes. And so they could not actually observe it to the full extent that they could have if the alerts came in earlier. So what we saw was a need for an early alert system. So GW 170817 was also found to be a source of short gamma ray bursts. So because of this event, we came to know that short GRBs are formed due to at least some compact object mergers. And so then the joint gravitational wave and such short gamma ray burst observations could be used to inspect a lot of deep astrophysics related to neutron star equation of state and the process by which these kilonovas are driven and the plasma jets and so on. So it's needless to say that these gamma ray bursts occur within seconds of the merger, and so it's important to actually look out for these types of mergers very early on, because it would one help localize the source and help with observations, and also the time delay between gravitational wave and electromagnetic signals, and also the pulse profile of these bursts can give us a lot of understanding of how the relativistic jet outflows happen and various astrophysical theories related to that. So for all of these reasons, it's important to observe them early on. Also, the early optical and UV observations can give us more knowledge about our process nucleosynthesis, which is a process by which heavier elements can be made, including gold. So all of the gold, this is one of the things that fascinated me when I was working on this particular event, that all of the gold that we see on Earth, all of this came from, all of this stuff actually comes from neutron stars. Gold cannot be made on Earth. And so another very good reason to learn about neutron stars. But I'm mostly kidding. But so early optical and UV observations also tell us a lot more about shock-heated ejecta. So also the prompt X-ray emissions can tell us a lot about final states of the remnant. And then observations in radio bands can tell us about the pre-merger magnetosphere interactions, help us test various models like that of BNSs being progenitors of fast radio bursts. So there are many, many astrophysical theories out there that can be tested well by early observations, or rather pre-merger observations. And such observations are also possible. And I'm going to demonstrate that by this slide here, this video here. So, so this video here, like, basically gives us an idea about how much longer gravitational waves from binary neutron stars are compared to just binary black holes. So GW 1708-817, our friend, you can see that at the bottom of the screen here, and that is compared to a few of the other BBHs, also our friends. But what you see here is GW 1708-17 was observable for more than 30 times longer than any of the previously observed gravitational wave signals. So I've been talking this whole time, and these events have merged. The signal is full, but here it still hasn't. It's still going. And the length of this video is almost a minute. So that's how long the binary neutron stars can last in our sensitive band. And this was just the third observing run, so we haven't reached our full sensitivity yet. So, so these VNS signals can be used to send out early alerts to multi-messenger partners because at design sensitivity, they are actually expected to last even longer, up to 10 to 15 minutes in the LIGO-Virgo frequency band. So early alerts sent out to astronomers can help them understand how to point their telescopes. And so then low latency searches can potentially send out such early alerts for BNS mergers even before they happen. So we ran some tests in using our offline searches, and we wanted to see if we can recover simulated signals of such binary neutron star mergers before the merger actually happens. So we tried to recover the signal at 58 seconds, so almost a minute before merger, 44, 28, 14, and then almost 10 to 0 seconds before merger. And all of these time cadences before merger actually corresponds to different frequencies because the frequency is increasing rapidly as we go towards merger. So in these frequency or time bins, we wanted to see if we can recover the signals, and if so, how well. So in order to do the study, simulated binary neutron star signals were added to some generated data, and we recovered them at different frequencies. And then we expected, so we computed some expected BNS merger rates, and then used that to compute the number of events expected in different frequency bands. And the key finding of this study was that at design sensitivity, we can observe 7 to 49% of total detectable binary neutron star mergers. And we can find them 60 to 10 seconds pre-merger, which means we can send out alerts before the merger even happens, like before the kilonova takes place. And then 2% of the total detectable binary neutron star mergers will be detected not only before merger, but also localized to within 100 square degrees. So astronomers will have a good enough idea about where to point their telescopes. And also we found that at least one event per year can be detected 10 seconds pre-merger and also localized to even less than 100 square degrees. So we want the sky patch of uncertainty to be as low as possible. So sending out early alerts in the present and future detectors will become key for multi-messenger astrophysics. And so in this animation, we show the evolution of LIGO's sensitive range between its initial LIGO and the present O4. Initial LIGO was before my time. This was like early 2000s, 90s. And then the range was like 15 megaparsec. And at present, so it kept increasing after that. So one was like 80 megaparsecs, and you can see how the observable universe is expanding, like observable to LIGO, that is. And now we are at 190 megaparsec. So O4 is not just scheduled, it's actually, it started in May of 2023, and then it's actually going to be the longest data taking period we've had so far, and we've just finished the first part of it currently. So, okay, so now we will transport ourselves to the future a little bit, and we will talk about future generation of gravitational wave observations using another type of detector called LISA. So we were talking all this while about ground-based detectors. Now let us see where the field will go in the future. So this picture here compares the sensitivities of various gravitational wave detectors that are planned or are currently operational. So as we know that the detection of gravitational waves from compact object mergers started with ground-based detectors like LIGO, but their sensitivity is limited by the lowest observable gravitational wave frequencies, which is about tens of hertz. And so NASA and European Space Agency's planned LISA will be a space-based detector that will not be limited by those ground-based noise sources that LIGO is, and hence it will have a higher sensitivity and will be able to probe the frequencies in the millihertz range, and it will make it sensitive to a broad range of astrophysical sources that we cannot see currently. And it also means that massive black hole mergers will be in band for several weeks, as against the few final milliseconds that we can see presently using LIGO. So a little more about what that will look like. So LISA will be a constellation of three satellites in space, forming an equilateral triangle with 2.5 million kilometer long arms. And the center of this constellation trails the Earth at a 20-degree angle, and its plane makes a 60-degree angle with the ecliptic. And this will be at a linear distance of 50 million kilometers from Earth. So what will this be able to see? So this figure here kind of motivates the type of sources that Lisa will be able to see. So it kind of shows the characteristic strain of the gravitational wave signals in the Lisa frequency band. The nominal detector sensitivity here is shown by this green line. And then displayed here are tracks of three equal mass black holes at a redshift of 3 with total masses of 10 to the 5, 6, and 7 solar mass. And then other sources are also shown in this frequency range, and this includes the LIGO type of binaries that we presently see the final few cycles of, and IMBHs, and these can be detected multi-band with LISA. And then we also have something called galactic binaries here, and then verification and MV harmonics, various types of objects that Lisa will be able to see. I'm not going into those details, but the interesting thing to point out here was the tracks of these equal mass black hole binaries show that they will be in band for Lisa for weeks to months before merger. So back in BNSs, we were getting excited about 1 minute. So here we are seeing weeks to months. So this figure was used for the LISA proposal, which was back in 2017, and it is kind of already out of date. So at present, we conservatively say that these massive black holes will be in band for weeks to months, but they may last even longer as our sensitivity improves as we get closer to launch. So the massive black holes could be observable for weeks to months in the LISA band. And if their mergers are electromagnetically observable, then it will be really useful for us to send out early alerts. So such mergers could be electromagnetically observable if they happen in active galactic nuclei. These are certain types of galaxies, and which are very dense. So in those disks, if the mergers happen, then the interaction with gases would lead to flares, and these flares can be observed optically as well as in X-rays, and they can also have gamma ray counterparts like the BNSs. So pre-merger alerts are then sent out to astronomers, could help multi-messenger observations, which can further our knowledge of astrophysics. So we want to do a low latency search for this as well. And so to execute a low latency search for massive black hole binaries, we use a publicly available massive black hole code, which is shown here. And it uses a stochastic search, which is the most optimal for large parameter spaces. And we run these codes under a Python wrap workflow for efficiency, which is what I'm currently developing. And then to test all of this, we use synthetic data, we use generated simulated data because we don't have data for LISA yet. And so our simulated data contains 15 massive black hole sources, much like the ones that we expect to observe, and 30 million galactic binaries in 1 year of stationary Gaussian noise. And so we just demonstrate our ability to actually search for one of these signals and send out pre-merger estimates of their parameters and sky maps. So this work is under progress, and we are working on the draft for the publication. And just for demonstration purposes, I wanted to show how the parameters change between 1 month before merger and like 2 days before merger. So we just wanted to take a look at a couple of these plots. So this slide here shows the plots for about a month before merger for one of the sources. And what you see in these small blue plots are probability distributions of the parameters like masses, the spins, etc. of the black holes. And you can see that these are not well peaked. We want them to be very peaked and pointing to just one number, but that's not what's happening here. And the sky map here, the red regions are where we expect the source to be. And you can see that it's not well localized. It's 15,661 square degrees, which is tens of thousands. So this is about 2 days before merger, and um, we see the PDFs are somewhat better peaked, and the sky localization also improves down to about 464 square degrees, which is an improvement of about a factor of 33. So just for context, we wanted to show the sky map for the full waveform after merger, and there the sky location should be about 264 square degrees. So going from months to weeks to days before merger, we get higher improvements. The simulated data here does not include higher than the fundamental order modes, and future releases would include these modes, and that will make the search more sensitive to such signals as they also enter the band earlier. So the analysis currently can be completed in the order of hours, and running over multiple cores and supercomputer clusters, it would take even less time, but we would still be dominated by the time taken to transfer data from the satellite to ground. So just some of the future and ongoing work. So I'm currently working on developing the fourth observing run offline and online analysis pipelines that involves designing of template banks, especially for the IMBH search again, and conducting tests and development. So on the other hand, for the LISA analysis, I would want to continue to work on developing the slow latency pipeline and conduct mock data challenges in real time so we can optimize whatever the pipeline needs. And in the run up to the LISA launch, we would need to deploy production ready search algorithms that can run on clusters and also send out alerts. So we need to figure out all of those systems, build collaborations that can help joint observations with the astronomers. And then, in general, this is not just my aim, but also that of the field in general. As we move away from the era of observing all these usual vanilla black holes, we will want to focus on observing more exotic objects that we currently cannot see as our sensitivities improve. And we will also want to start to interpret the astrophysical implications of what we are observing and what these observations actually mean. So learn to do more physics with it. And so a little bit more about the field and its journey so far. So the LIGO founding members were awarded a Nobel Prize in 2017 for the discovery of gravitational waves. The LIGO members also shared a breakthrough prize for the same. I was a part of the group that discovered the gravitational waves for the first time, and that's actually exactly when I began my PhD. So I did some small tasks, but I was really excited to have been a part of that work. So it's a very young field in that sense, and it's taken off from there. So I'm there in a lot of I was a part of a lot of those initial discovery pieces and did work with those groups. And so the discovery of supermassive black holes, also by a separate group, received a Nobel Prize not very long ago. The start of the multi-messenger astronomy with gravitational waves with the observation of 170817 has led to a breakthrough New Horizons Prize so far, besides several grants and awards. And we have a lot to learn from the joint observations of gravitational waves and gamma rays, and in general, other multi-messenger channels. And we don't want to miss the bus on that. We do have some women in the field now, but we would like to see a lot more than we do currently. And then, very excitingly, as of last Thursday, I'm happy to tell you, the LISA mission just got confirmed by NASA and the European Space Agency. And this is particularly exciting because there was a time about 10 years ago, my seniors tell me, when the mission was actually scrapped. So they didn't even know if this would actually get confirmed, but now it is, and it is set to launch in 2035. And it's going to be hopefully our mission possible. So it is the first talk that I'm sharing this information in, and I'm happy to talk about this. This looks like an exciting future in gravitational waves. If you guys are interested in the field, you're interested in career, the aspects of physics research in general or gravitational waves in particular, I'm very happy to talk about that. Career counseling is one of my favorite hobbies. So please ask. I was very confused at your age about what to do, where to go, which coaching to go to, which exam to take. I can tell you some of the things that I have done and been benefited from, for sure. So, and in the end, I would like to kind of end with this quote that I like from one of the Nobel laureates um, in gravitational waves. And he said at that time, and that was a while ago, that we can actually begin to see the whole universe in black holes. And in my career, I'm beginning to find that to be more and more true. We are beginning to learn more and more astrophysics because of these black hole detections. Okay, thank you. And I'm happy to answer questions.
Wow, that's fantastic. So exciting. Thank you, Devnandini, for that awesome talk. And it was a lot of information. I'm so sure some of it is quite dense for some of the kids here. I also see some really young kids, like fifth grade, sixth grade kids. We have some questions in the chat. Let me quickly go through them. So one of the question is actually related to the gold. So you were talking about the gold. Can you say a little bit more on that? It's coming from the neutron stars you mentioned.
Yeah, so what happens is the kind of temperature conditions that are needed to make fusion possible to go up to gold. So there's something called binding energy curve in nuclear physics, which tells us the sequence in which a nuclear fusion can occur to give us newer elements. So I don't know the background of the student who has asked this, but on okay, so on Earth, we can only fuse things to go all the way up to iron. And then after, we don't have the energy conditions needed to make elements above that.
Mhm.
And so neutron star, like, the rest of the elements all come from stars. And so, this is a bit philosophical, but I like this philosophy. It's like you will see the saying in a lot of places that we are made of stars. And the meaning of that statement is this, that a lot of these elements are not made in Earth, they are made in neutron stars. And gold is a particular type of reaction leads to the formation of gold, and that is what is called our process nucleosynthesis. And so that happens during events like the kilonova explosion that we saw a simulated video of. So it takes very energetic events to give rise to elements as heavy as gold.
Wow. And next question is from Alolika Mondol. Alolika asks that could you please explain us the term space interferometer?
Okay, so again, this is something you will, I think, study in undergrad college, undergrad physics courses. So Michelson interferometer is basically an instrument that is used to interfere light, and the principle there is the same, that when the light beams interfere constructively, you will get you will get like a larger resultant, a larger amplitude. But when they interfere destructively, which means they are not in phase, you will not get a light output at all.
Okay, so now let's take a question from Mrinalini Biswas. She has a raised hand. Go ahead and mute yourself.
Actually, I have three questions.
Okay.
So, I'm a student in grade six. So, like, what should I do to get into astrophysics? Like, which exam should I do? I have to crack, or courses I have to pursue?
Okay, so as so you're in sixth grade. So I would say the first step would be choosing science as against commerce or arts when you get to select that. That's usually around class 8, or in my time it was class 8. It could be earlier now, but 8 or 9. So this is for your 10th board. You should go for science, and then same thing for 12th board. You go for science, but the question is what about after that? So for me, I went into physics honors, BSc physics honors course, and I went to University of Delhi. I did my bachelor's and master's from Hindu College. So you can go to any standard university in India for this. And so Delhi University typically accepts students on the basis of your PCM average, your physics, chemistry, math average. And there are cutoffs, like every college has its own cutoff grade. But then again, there are colleges where you have to apply for an entrance exam and clear that. So, for example, in Bengal, the institutes like Jadavpur, most of the Calcutta University colleges, Presidency, I think they mostly do entrance exams. So different colleges have different systems. One advice I'll have for anyone here is try to choose a college or a bachelor's or master's program where you get a GPA grade. GPA is grade point average, and GPA grade has that one big advantage that you are not just getting the number of points that you score. For example, if out of 100 you get 80, and 80 is the highest in the class, then a regular university will just give you 80%, but that doesn't say anything about you. But if you get a GPA score, then you in India usually GPA is out of 10, in the US it's out of 5, but a grade point average score takes the performance of the rest of the class into account. So you will an 80% that's highest in your class will show up as a GPA of 9 or 10. Whereas, so that would tell an external person who is not from your university, someone who's recruiting you, someone who's giving you admissions, it will tell them that you were the best in your class. But if you just show them a mark sheet that says 80%, it doesn't help, it doesn't show you in a good light either. So these are things that I did not know. So that's one thing. So you have entrance exams to get into bachelor's or master's programs, and so then the path is that way. So after masters, if you can apply for a PhD program anywhere in India or anywhere in the world, and again, for PhD entrances, you have to take an exam, an interview, and you get into the program. You also have to apply for fellowships. So, so it's a long process that way. And it's after your PhD you do postdoctoral research, which is where I am. And again, that's interviews and exams that you have to clear for that. So I can. This is like an overview of things. I can answer more detailed questions about each step if you want.
Uh,
Awesome.
I
Yeah.
have like two more questions.
Okay, go ahead and ask one more, and then I'll have to ask someone else. But go ahead, ask one more.
So is has anything been found like inside black holes? Is there any details about that?
Inside black holes, no. We
Okay.
don't know what's like inside black holes. We only have mathematical theories about the inner structures of black holes, but the thing about black holes is we cannot get any information out of them yet. So we can't inspect what's inside.
Okay. Thank you.
Okay, let's go ahead and ask a question. Open a question from Arav Jain. So, hypothetically speaking, if wormholes and Einstein-Rosen bridges existed, do we have any way of detecting these celestial objects? Or are we planning for any methods in detail that may be formed in the near future?
So about wormholes, yeah, no, not at the moment, but that's again, those are very theoretical concepts that we don't have any proof for. So I think the proofs of this sort would come from lensing patterns, gravitational lensing, which is if you have black holes or high gravity objects, then the space-time around it curves in a certain way, and so it bends light in a certain way. So that's what can be detected. But with our current planned detectors, wormholes are not our targets.
Great. So I have a lot of questions coming in, but we do have to finish up this particular session now because there is another session coming up after this. But what I would like to say to all of you, please send your questions to Chinta admin, or if you know me personally, just WhatsApp them to me, and I will bug Debnandini with some of these questions, and I'm sure she'll be happy to answer some of them. And maybe in future, I saw one amazing thing, Debnandini, I must congratulate the kids as well. I see 56 plus kids here in this session, or 50 plus kids are here, and most of them are like little kids, like fifth grade, sixth grade, seventh grade kids, and they look through an entire thing. Some of it is very dense for me as well, but I'm sure that they stuck together, so which is awesome, I think. And in some future, if we can get your time again one more time, then that would be really awesome as well.
So, what's the standard attendance of your other talks of this nature? I'm curious now.
So it depends. For example, last week we had a session with a student from ISC Bangalore where the discussion was around 40. And there was usually theoretical math has much lower attendance. But physics is awesome. People are excited about it, and we are discovering stars and everything. So that I think really is exciting. But yes, I think 50 plus is actually a very good attendance in our context. And some of the students are actually from Alolika, for example. I think she is from the school in Purulia, and there are I see a couple of people from Sundarbans as well. So they, it's a bit late, I think, for them. That's why maybe some. Otherwise, many more people would have joined from those regions as well. But of course, I'll be putting this up on YouTube, and anyone can see it.
Okay, thank you everyone for coming and coming in at this very late hour to listen. Thanks
Thank
a
you
lot.
again, Debnandini. It's awesome to have you. Take care. Bye.